In this video, we're going to discuss the lab, finding the specific heat capacity. If we look at our table, what we asked was that you were going to pick a metal sample, any one from 1 to 6, and let's say that you picked metal sample 3. Then you were going to work through the trial and gather your data for metal sample 3. And when we did that, if you remember, because the cubes were so small, we were asking that you took 2 of the cubes and just kept them together through the entire trial. Then we were going to have this as trial 1 for metal sample 3, then this as trial 2 for metal sample 3. Then you'd pick a different sample, maybe you picked 5, and then this would be trial 1 for metal sample 5, and then trial 2 for metal sample 5. So that way we get 2 trials with each of the samples that you chose. Here it asks, before doing these types of calculation, it is usually helpful to draw and label various parts. So we're going to draw the calorimeter and the metal inside, so you can have a drawing here. And the important thing about the calorimeter is that we are trying to isolate whatever takes place inside this calorimeter in order that no energy will be coming in or out of the calorimeter. It is essentially a fancy ice chest. And in this area right here is styrofoam, not allowing any energy from the outside to get in or energy from the inside to get out. And then, of course, we have our, and you'll do a much better job drawing this than I do, but we'll have our thermometer in here and our stirring rod. And then it says, we're going to label the water, so we're going to put some water in here, and we're going to place our 2 cubes. Obviously, they'll be sitting on the bottom of the container, but 2 cubes in here. When you first placed the metal in the calorimeter, which way was the energy moving? Well, we're going to say the energy was moving from the metal to the water because the metal is at a higher temperature, as we discussed in the previous video. Because the metal is at a higher temperature, the energy will flow out. The metal will lower in temperature, the water will raise in temperature until they finally reach the same temperature. Once they reach the same temperature, we call that thermal equilibrium. Thermal equilibrium is a fancy word for they have finally reached the same temperature and neither one is going to change temperature anymore. On the side of the diagram, write the following information. So we're going to write the information. We only need to write it for one trial, but we want to label them. So first we're going to label the mass, and we're going to write mass, and then as a subscript we'll write the mass of the metal, and that will be in grams. Make sure that you choose to write your units, and I'm only going to write these for one of the trials. We'll do all calculations with all of them on the next page, but just as an example. Change in temperature of the metal and change in temperature of the water. Notice how they do this. Change in temperature of the metal and change in temperature of the water. Notice the subscripts are not only useful but required so that I know which one I'm talking about. Now remember, your metal probably started, the initial temperature of the metal probably started about 100 degrees Celsius. I'm hoping that you measured this, and I'm hoping that you measured it to the nearest tenth. Our thermometers are calibrated to the nearest tenth. So we should be writing 98.5 or 100.3. You should be going to the nearest tenth. Then there was an initial water temperature that was probably around 20 degrees Celsius, maybe 21, 22, 23. Once again, that should be measured to the nearest tenth. Don't give me any whole numbers here. And hopefully at this point you're not just having to put 0.0 on there, because it will affect your data on the next page. Notice the metal's temperature reduces, the water's temperature increases until they finally reach the same temperature. One keeps going down, one keeps going up until they finally reach the same temperature. It was probably approximately 30 degrees, but once again, make sure that you measure to the nearest tenth. Our thermometers are calibrated to the nearest tenth. So when you're dealing with the metal sample, it started at about 100 and went all the way down to 30. But when you find the change, it's always the final subtract the initial. Well, in this case, the final is going to be less than the initial, so your metal is going to have a negative degrees Celsius, whatever the subtraction is of these, probably be about 70 or so. Now for the water, the final subtract the initial, that's going to be a positive degrees Celsius, because the final is higher than the initial. So that's okay to have a change in temperature of the metal as negative, change in temperature of the water as positive. Notice their change is not the same. The water didn't change much temperature. The metal changed a lot. Do we know why that would be? Well, because it's the same amount of energy. The reason being is water has a very high specific heat capacity, so it will not change temperature very easily. But all the metals have low specific heat capacities, and it will change temperature quite easily. Then, the specific heat capacity of water, when we look up the specific heat capacity of water, I know they just used a W here for the water, and I just wrote out water. Same with M, they used, and I wrote out metal. So I look up the specific heat capacity of water, and the specific heat capacity of water is 4.18, but I need to have units on that, and it's joules per gram degrees Celsius. We will all use the same water specific heat capacity and not have different values. That's why I put lines here but not here. And then the specific heat capacity of the metal, but we don't know what that is, so that's our question mark. That's our goal. That's what we're trying to find, is the specific heat capacity of the metal. That way we can go to this page and find out what the metal is made out of. So that's what this page would look like. Then, on the next page, we're going to answer a few questions. A change in temperature requires the molecules to speed up or slow down. Does this temperature change during a phase change? Explain. Remember the heating and cooling curves. So I want to remind you, and once again, we're going to be taking, I'm going to show notes, and then you'll turn it into paragraphs. But remember, when we're talking about a heating curve, we have this angled piece, then we have this flat piece, we have the angled piece, flat piece, angled piece. Remember, this is only solid, this is only liquid, this is only gas. This is the solid changing between the liquid. This is the liquid changing between the gas. So, a change in temperature requires the molecules to speed up or slow down. Yes, whether you're a solid, whether you're a liquid, or whether you're a, that should be a gas, it doesn't look like it, or a gas, there is a change in temperature. Does the temperature change during a phase change? So they're talking about this right here, solid to liquid or liquid to gas. The answer is no. We can either have a change in temperature for a solid, for a liquid, or for a gas, or a change in phase, change in phase, solid to liquid or liquid to gas, but we can't have both at the same time. We can't have a change in temperature and a change in phase at the same time. You can only have one or the other. In our lab, did the temperature change and why? Well, there's two things that we're dealing with. We're dealing with the metal and we're dealing with the water. And remember, it's the water in the calorimeter that we're dealing with, not the boiling water that heated up the metal. We're just looking at the water in the calorimeter. Well, the metal did not turn to a liquid. It did not turn to a gas. So it was a change in temperature. The water in the calorimeter, remember, we're only dealing with the water in the calorimeter, it did not boil and it did not freeze. Remember, the boiling water is something separate. We don't need to worry about that. All it was used to do is heat up the metal sample. So when we talk about the water, we're only talking about the water in the calorimeter. And it did not freeze and it did not boil. So it also only went through a temperature change. Use the proper notation and write the mathematical equation you would use to find the heat energy of the water. Notice they're looking for the water here. Now, we can reference back to our graphic organizer, and we look at our graphic organizer. And when we look at our graphic organizer, both of these are a change in temperature. The water, or actually, let's look at the metal first. The metal change in temperature is down here because it's a solid. When we look at the equation for the change in temperature of the metal and the water, so let's go to the water first. Here's the water. The change in temperature of the water is in section C because it's a liquid. And when we look at that equation, the equation looks like this. The amount of energy of the water equals the mass of the water multiplied by the change in temperature of the water times the CP value of the water. There's our equation for a change in temperature of the liquid of the water. It didn't freeze and it didn't boil. Now, for the change for QM, the amount of energy of the metal, now we're down here in section A. So we look at the equation for section A, and the amount of energy for the metal equals the mass of the metal times the change in temperature of the metal times the CP value of the metal. Now, we know, we just discussed the idea that energy is conserved. That's what we did on this previous here, conservation of energy, question number 5, that any energy that's being lost or technically given away by the metal has to be equal to the amount of energy gained by the water. These two must be equal. So that's what we're looking at right here, where the amount of energy that's being given away by the metal has to be equal to the amount of energy absorbed by the water, based off the conservation of energy. So now we're going to set equation 5 and equation 6 equal. So we're going to say QW is equal to QM. Well, QW is this right here. So on this left side, MW times delta TW times CPW is equal to mass of the metal times change in temperature of the metal times CP of the metal. Write the equation from 7, substitute the numbers from question 2, and use 4.18 as a specific heat of water. So, here's the idea. When we write this equation, M of the water times change in temperature of the water times CP of the water, I'm just rewriting this equation. The only one that we don't know is this one right here. This is our unknown value. So we're going to solve for this, which means we need to make sure that it's on top and that it's by itself. So I'm going to divide this side by m mass of the metal and change in temperature of the metal. Divide this side by the mass of the metal times the change in temperature of the metal. These two cross out. And now if I rewrite my equation, Cp of the metal, it should equal the mass of the water times the change in temperature of the water times the Cp value of the water, all divided by the mass of the metal times the change in temperature of the metal. And when we do all of that, we should get our answer in joules per gram degrees Celsius. And then what we're going to do is we're going to be able to find this value on the back side of our chart, and with the also possibly the color, now we're going to be able to identify the type of metal that it is made out of. Now, we're going to do this calculation not only for the one metal of trial 1, but also trial 2, and then trial 1 and trial 2 of the other metal. And you're going to use both of those values to determine what the substance is. Then you're going to do the same calculations. I need to see these numbers. Now, in the next step, you would have shown me what numbers you're actually putting in here. So I should have pushed this down to the bottom and given space for you to actually put the numbers in and show me. I need to see what numbers you're putting in. So you're taking these values and putting them into here. Now I've noticed that the one value that's not shown over here is the mass of the water. And that is up here also, the mass of the water. The way that we find the mass of the water is we have the volume of water. And if you remember, that was between 110 milliliters and 130 milliliters. You would have measured that using a graduated cylinder to be very precise. And then knowing that the density of water is 1 gram per milliliter, however many milliliters you have is the number of grams. So however many milliliters you have here is also the number of grams here. So the mass of the water is also there in grams. And now you can use that value and show me putting those numbers in and getting that information. Depending on how much space you use, you're probably going to need to use a separate page to show me the numbers. I need to see the numbers here for each of the other 3 trials. We have 3 more trials, trial 2 of this, and then trial 1 and trial 2. So you'll do that on a separate page and then include that in so that I can see that. I hope this helps with the calculations from your data table in the specific heat capacity lab.